Hello and welcome back. Do you remember how back in 11.2 we proved that a geometric series converges when r, the common ratio, is between -1 and 1? In other words, when r, the thing that you're multiplying by to get the next term of the series, is a proper fraction, then the geometric series will converge. Well, it turns out that in general, for a series with positive terms, if as n approaches infinity, the next term is a fraction, and by fraction I mean a proper fraction, something less than 1, so like a half or even 2/3. If it's a fraction of the previous term, so if you compare the next term with the previous term, and the next term is a proper fraction of the previous term, and if that's always the case, then the series will converge. This is essentially what the ratio test says. It says that if the series acts like a geometric series, then it's going to converge or diverge like a geometric series. So here's the ratio test. It says, suppose that you take the limit as n approaches infinity of the next term over the previous term. So a sub n plus 1 is like the next term, and then a sub n is like the previous term. So these are two terms that are right next to each other. I might consider calling a sub n like the current term, and then a sub n plus 1 like the next term. You can think of it that way. And then we're going to put some absolute value bars around this to make this expression positive. And suppose you get this limit is equal to L, well, where in this case L will be, again, some positive number. It could be positive infinity as well, so we're going to consider that case. But based on what L is, that's going to tell you if the series converges or not. So if L is less than 1, that means a proper fraction, somewhere between 0 and 1, so a half or a tenth or 2/3, then the original series is going to converge absolutely. If L is greater than 1, or if L is infinite, so if you get infinity here, then the series is going to diverge. And if L is equal to 1, well, in this case, the test is inconclusive. It's possible it converges, it's possible it diverges. We're not really sure. We have to try something else in that case. So here we're riding on the fact that the series is acting like a geometric series if when you take the next term divided by the previous term, you get more and more like this fraction L. So if L is a fraction, the series is going to converge. If L is a proper fraction, I should say. So if L is like a half, basically you're multiplying by a half to get the next terms. Maybe not exactly a half, but close to a half, closer and closer to a half to get the next terms. And then it's going to be acting a lot like a geometric series with a common ratio of a half. So you can think of L here as being like your common ratio, right? If L is a half, you're going to have a convergent series. If L is 5, then essentially you're multiplying by 5 to get the next term of the series, and that's going to blow up to infinity. So in that case, the series would diverge. So you really want to think, to understand intuitively what the ratio test is saying, you want to think about how it's telling you how a series acts like a geometric series. And that'll explain why these L values have to be less than 1 for it to converge and greater than 1 for it to diverge. Now it actually tells you in the case where L is a proper fraction that the series converges absolutely. And remember from a previous video that if the series converges absolutely, then it converges normally. So if it converges with the absolute value bars, it converges without the absolute value bars. All right, so enough talk about that. Let's head into example 4, where the rubber hits the road. I don't know where that came from. So we're asked in example 4, does the series n equals 1 to infinity of 2 to the n plus 5 over 3 to the n converge or diverge? Now in this case, you could break this up into two separate fractions, and you'll get two convergent geometric series. But let's go ahead and try to show this using the ratio test. So what we'll do is we'll take a limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Remember the a sub n's are the terms, so a sub n here would be 2 to the n plus 5 over 3 to the n. Now in this case our terms are all positive, so we don't really need those absolute value bars. We just have 2 to the n plus 2 to the n plus 1 and then plus 5 over 3 to the n plus 1 all over the a sub n's, which are 2 to the n plus 5 over 3 to the n. Oops. And when you divide by a fraction, it's like multiplying by the reciprocal. It's the same thing. So we have 2 to the n plus 1. Did it again. And then times the reciprocal of a sub n. Okay, there we go. Now what we can do is try to simplify. Looks like there's a 3 to the n that can cancel on top and bottom, right? N of these factors of 3 on the top will cancel with n of these factors of 3 on the bottom, and you'll have one factor of 3 left on the bottom. Now, you can't do the same things with the 2 to the power of n and n plus 1, because those aren't factors. You still have that plus 5 to deal with. That's not too bad. Let's see what we have so far. Now we've got the limit as n approaches infinity of 1/3, separate that out, and then 2 to the n plus 1 plus 5 over 2 to the n plus 5. Okay. Now what we've got is an infinity over infinity situation. Now we could use L'Hopital, but we could also divide top and bottom by the leading term of the bottom, which would be 2 to the n. And when you do that, suddenly my voice got out of control. When you do that, turn into an opera singer. I hope my wife is not listening outside the door right now. We will get, 2 left over from when we do 2 to the n plus 1 divided by 2 to the n, and we get 2. And then 5 over 2 to the n. And then on the bottom, we'll get 1 plus 5 over 2 to the n. All right, now, each of those little fractions are going to go to 0 as n approaches infinity, because the 2 to the n will blow up to infinity. 5 over infinity is going to go to 0. Same thing with the fraction on the bottom. So you eventually just get 2/3. So 1/3 times 2, which is 2/3. There we go. Now, what did we just do? Besides singing opera. We just found the limit as n approaches infinity of the next term over the previous term to be 2/3. 2/3. So basically, as you go far out in the sequence, you're essentially multiplying each term of the sequence by 2/3, or some number close to 2/3, to get the next term of the sequence. So this series is acting like a geometric series with a common ratio less than 1. So this series is going to converge by the ratio test. And that's it. And actually, we know that it converges absolutely. So we know that more so than even just converging, it converges absolutely. It converges with those absolute value bars on. When we stuck these absolute value bars on, and we got this limit here, we know that it's going to converge absolutely. All right. Let's check out example 5. Example 5 has a series that's yelling at us here. A series with lots of factorials. We've got this series n equals 1 to infinity of parentheses 2n factorial over n factorial n factorial. So does that series converge or diverge? And it turns out that the ratio test works really well with factorials. You'll see in a moment why. Well, we'll start with what we always start with the ratio test. The limit as n approaches infinity of a sub n plus 1 over a sub n in absolute value bars. Now, what I'm going to do here is, first off, note that the terms are all positive. There isn't any negative sign to be found here, so we can drop these absolute value bars. The second thing is that whenever you have this fraction for your terms, which you're almost always going to have, then the a sub n plus 1s, that fraction divided by the a sub n fraction, remember that just a moment ago in example 4, dividing by that fraction is like multiplying by the reciprocal. Now we wrote it out in 2 steps in example 4, but let's go ahead and just write that from the beginning in example 5. We're going to write the a sub n plus 1, which is like the a sub n, but just with a bunch of n plus 1s plugged in instead of n. And then instead of doing divided by a sub n, we're going to multiply by the reciprocal of a sub n. So by the reciprocal of our original terms. N factorial over 2n factorial. All right. Now it's time to simplify. And these factorials, are they ever going to simplify? So here, the n plus 1 factorial and the n factorial are very close to each other. Remember what a factorial looks like. So 5 factorial is 5 times 4 times 3 times 2 times 1, right? That's what a factorial means. It means you start with that number and you multiply by all the numbers that come before it. Well, notice that what you could do is you could take just the first factor of the factorial, and then the rest of it you could write as a factorial. You could write this as 5 times 4 factorial. So 5 factorial is the same thing as 5 times 4 factorial. Because you can write that tail of the factorial as just a 4 factorial there. In a similar way, you can write n plus 1 factorial is equal to the first factor, n plus 1, and then times all the rest of the factors written as a factorial. So the next term, the next factor would be n, and then the factorial would give you all of the factors that come after n minus 1, n minus 2, n minus 3. Remember the factors get smaller by 1 all the way down until you get to just the last factor, which is 1. So in essence, you're popping off that first factor of n plus 1 and leaving the rest of the factorial as a factorial. All right, we can do the same thing, it turns out, with 2 times n plus 1 factorial. So this is the same thing as 2n plus 2 factorial. Distribute that 2 into the n and the n plus 1. And now if you think about what this factorial looks like, well, it's going to be the first factor times the second factor and so on. Now our goal is to eventually cancel off with this 2 times n plus 1 factorial with this 2n factorial. So we want to stop when we get to a factor that looks like 2n. So we're going to write the first factor. The next factor is 1 less. So that's going to be 2n plus 1. The next factor is going to be 1 less than that, which is 2n. And we could continue on, but remember we're going to try to cancel off this 2n factorial on the bottom, all those factors. So we're going to write the rest of them as just 2n factorial. Okay, let's write out what we have. So we have the 2 times n plus 1 factorial. That becomes 2n plus 2 times 2n plus 1 times 2n factorial. Then we have the n plus 1s. Each one of those we popped off an n plus 1. And we're left with n factorial. And then the rest of it, the a sub n part of it, or the reciprocal of the a sub n's. Let me write that. There we go. Good enough. Looks like that. It stays the same. So now we get to have a big canceling party where we get to cancel off the 2n factorial with the 2n factorial, the n factorial with the n factorial, this n factorial with this n factorial. All kinds of stuff is just canceling and just having a great time canceling. Now what's left we're going to distribute out. We're going to write this as 4n squared plus 2n plus a 4n, that's 6n plus 2, over n squared plus 2n plus 1. And we're distributing everything out because when we take this limit, we can think, oh, okay, we'll just take the leading terms here. The top is going to infinity, the bottom is going to infinity. And we could use L'Hopital if we wanted to here. But we can also divide top and bottom by the leading term of the bottom. and then take the limit as n approaches infinity. All those little fractions will go to 0. You'll end up with 4. Now again, this is your common ratio in essence. This is what you're effectively multiplying by to get the next term of the sequence, of the series. And this is going to be basically multiplying by 4 every time you want to get the next term of the series. So these terms are going to be blowing up to infinity. And that's going to make the series blow up to infinity. Or you can also say, because this is acting like the common ratio here of 4, and that is greater than 1, so greater than 1, then, write it over here, then by the ratio test, our series diverges. There we go. Thanks so much for watching, and see you in the next video where we're going to talk about the root test.